Hello and welcome to a new video by the Science Wizard. Today I'll be covering complex numbers, and you'll see they aren't quite as complex as name implies. We'll start with normal numbers like 1 or -5, 3.5, pi, square root of 2. These are all normal numbers. You can give them a value like pi is 3.1415 and so on. Square root of 2 is 1.4 something. Now, every single one of these numbers, from minus infinity to positive infinity, you can imagine on a line. This was called the number line. Since you were a kid, you probably heard it in class. It's the number line. This is 1, around here is -5, 3.5 around here. Here you have square root of 2. Pi is around here. You've seen this. This isn't new. But now, we'll take a closer look at the square root. Because you've seen you can only take a square root of positive numbers, even positive rational numbers. Even square root of pi exists. But you couldn't take a square root of a negative number. -1, for example. Now, this is where the imaginary part comes in. We'll assume you can take the square root of a negative number, and we'll call it I, or J if you're an electrical engineer. But for now, we'll continue with I, because J is only used in certain branches of science and isn't commonly used. So, now, the definition for I. I is commonly defined as I squared equals -1, because scientists still don't like this form. But I can understand why, because you've been you've been taught the square root of negative number, you can't have that. But this is, well, for some reason this is good. Now, we'll go back to this line. I'll delete this one and bring this over. Now, here on this line, where do I put I? Can I put it here? That would be around 2. No, can't. So, what we'll do, we'll just give it a new axis. This is the real part. This is the imaginary part. And around here is I. And if you want to write a complex number, this for example, you'll see what the value is on the imaginary axis and what the value is on the real axis. And this would be, let's say, pi plus I. You can see it here on the plane. It's a number. Now, how we'll define these imaginary numbers, or complex numbers rather. You have an imaginary part and real part, and the imaginary part is always I times something, and the real part is just another number. We put these together in the form z equals a plus ib, where z is the complete number, a is just the real part of the equation, and b is just the imaginary part. Note, b can be imaginary itself. B has to be real because you already put an I in front of it. Now, some examples. For example, 1 plus I. 3 plus pi I. Or I pi, because I is in front. Doesn't really matter. You can write it like this. Just, this is common use term. Something else, like pi plus IE. Still exists, still is a number. Now, we have these numbers, but what can we do with them? Well, first let's look at some things we can do with them. We have addition, like two normal numbers, like 3 plus 5 equals 8. If we use complex numbers, we'll just use a plus ib plus c plus id. And this will just become a plus c for the real part, plus I times b plus d. If you want subtraction, you can just use minus. So for minus, 3 minus 5 would be minus 2. For a plus ib minus c plus id would be a minus c plus I times b minus d. Nothing wrong with that. Now, multiplication. It's gonna be a little more complex because, well, now for multiplication, we have a plus ib times c plus id. And we all know this rule. I'll give another color for you guys. A times c plus I times AD plus I times BC plus I squared times BD. And what this will become, you'll see, because we have this I squared here. And what we knew from before, it's the definition of I squared, it's minus 1. So we can rewrite this as minus BD. So now in a whole, we'll have AC minus BD, put the I in the front, plus I times AD plus BC. And it's still a complex number. Now, of course, if A times D plus BC equals 0, you have a real number. That's just some cases. And now the really tricky parts, division. How are you gonna do it? Now this is gonna be a lot harder because A plus IB divided by C plus ID. Well, you'll see you can't just divide it by a sum. There are some rules, you can do it. It's just not so simple. So what we'll do is we use technique called multiplying by the complex conjugate. You see how this is C plus ID? Its complex conjugate is C minus ID. Now, of course, multiply both top and bottom, so doesn't change the value. And then we'll just use multiplication as seen here. So this will be AC. Now, look out, because it's a minus, not a plus. AC minus IAD plus IBC. And then this will be minus I squared, which will be plus. So plus BD. And then this here, it's the form of A plus B times A minus B, which you'll probably have seen in class, equals A squared minus B squared. But since B squared isn't just B, it's I squared B, or in this case, I squared D squared. And minus I squared is just plus, so this will become C squared plus D squared. And since this is a value you can calculate, it's just each individual divided by this number. To put this in a better form to read, it's AC plus BD divided by C squared plus D squared. And then plus I times BC minus AD divided by C squared plus D squared. Now, this in general is the formula you can use, but I ask of you, don't remember it, because I want you to remember the method we used. Just multiply the upper and lower part of the division by the complex conjugate of the divisor, and you can just go from there. It isn't that hard to see. You see, it's one step, maybe this is the second step, 3 steps, maybe 4. Not that hard. Now, while this is a valid method, isn't the best one. Let's take a look at this. When we have the plane, this is also known as Gauss's plane by this awesome guy, Gauss. When we have a number, let's say this is 3 plus I4. We can define it by, here you have 3, here you have for I or I4, doesn't really matter. You can also define it as the distance from the point to the null point and the angle. In this case it's theta, and the distance we'll call r. Now, how do we put this in a formula? This is just called the polar form of a complex number, and the form we use, or at least the formula we use, z equals r times e to the I theta. This can be proven, but I don't really see the point in proving that. If you want to, ask in the comments. I can make a separate video. If not enough people ask, then I won't make a video. You'll just have to look around a bit. It's not that hard. Maybe you can even define it yourself, try it yourself. It's a fun exercise. But now, this formula. What we see here is we don't have a plus. We don't have two parts. We have multiplication. So if we want to divide two numbers, you have z1 divided by z2. That will become r1 times I to the theta 1 divided by r2 times e to the I theta 2. And what you remember from class, at least I hope, this will become r1 divided by r2 times e to the I theta 1 minus theta 2. Not that hard. Now I've just given you this polar form, but how do you convert from the polar form to the Cartesian form, which is a plus ib? Well, when you look at this drawing over here, you can see r is the hypotenuse of this right triangle. So using the Pythagorean theorem, you can see 3, well, this is 3, or in the normal case, a squared plus b squared equals r squared, or r equals the square root of a squared plus b squared. Now, how do we calculate theta? We'll use the definition of the tangent. So the tangent of theta equals 4 divided by 3, or in the normal case, b divided by a, imaginary divided by real. So theta equals the reverse tangent, or the arc tangent, of b divided by a. That's how you can convert from polar to Cartesian. But if you want to go the other way around, it's also possible. We'll look at the drawing again. Now you see you have r and you have the angle theta. If you want to go down, I hope you remember basic trigonometry. You have this circle, 1, 1, minus 1, minus 1. Then this is cosine, this is sine. And well, in this case this is 1, but it could be r. So a, or the real part, equals r times the cosine of theta, and b equals r times the sine of theta. Now that I've taught you how to solve problems like these, let's solve some problems like these. So 5 plus 3 is 8, divided by 4 plus 3y. Now this is division, and we've seen it's better to convert to the polar form. So what we'll do, 4 plus 3, you can see Pythagorean theorem, it's 5. If you don't see it, it's 4 squared plus 3 squared equals 16 plus 9, square root of course, it's 25, square root of 25, that's 5, times e to the I arc tangent of 3 divided by 4. Now we don't know the exact value, doesn't really matter. Now this is a divided by 5 times e to the I minus the arctangent of 3 divided by 4. Now we want to convert it to the Cartesian form, and this is 8 divided by 5 times, first you have cosine of this angle minus the arctangent of 3 divided by 4 plus I times 8 divided by 5 the sine of minus the arctangent of 3 divided by 4. Now, a formula exists for this. I won't show it here. If you want to, I can give an explanation. I've also used this formula for the cosine of a arctangent in this case, or the sine of an arctangent. I've used it in the Quiet Kid Makes his exams video. If you want an explanation, I'll make one. But for now, we'll just use the formula. And it's 1 divided by 9. Wait, before we do that, first we need the minus gone. Cosine of negative angle is just positive. Negative angle of a sine is also negative this sine, so it's negative. And the positive angle. Now we can use the formula, which is 1 divided by 9 over 16 plus 1 minus I times 8 divided by 5 of 1 over 16 divided by 9 plus 1, which is 8 divided by 5 times 1 over, this is 16 over 16, so it's 25 over 16 minus I times 8 over 5, same case, this is 9 over 9, so it's 1 over 25 divided by 9. Now this will be 8 over 5 times, this is 4 over 5 minus I times 8 over 5, 3 over 5. This is 8 times 4, 32 divided by 25 minus y times 8 times 3 is 24 divided by 25, and this is the answer. Now for the next one, 5 divided by 3 plus 5. Now if I see 3 plus 1 isn't really a Pythagorean form, I know. So for this, also to show off the other method, I'll use the complex conjugate. So it's 5 times 3 minus y divided by 9 plus 1, which is 15 minus I5 divided by 10. So this is 1.5 minus I 0.5. This is, well, not too hard, not too easy. Now if we look at the next question, it's 3 plus y divided by 5. Now this is a whole lot easier. You can just split it. It's 3 divided by 5 plus y divided by 5. You can see the difference. It's a bit more easy. Now remember, if you have 1 divided by a plus b, this does not equal 1 divided by a plus 1 divided by b. This is not the case. It's the case for some values, but it's not always the case, so don't use this. It's a common mistake. Please don't forget this. Next one, 4 plus I squared. Now, we haven't seen how to square these numbers before, but I want you to try. Just pause the video, like you've hopefully done with the other exercises, and let's try to calculate it yourself. Now, this is 16 plus, and then 2 times ab from the formula a plus b squared equals a squared plus 2ab plus b squared. And you'll see this is 16 plus 2 times 1 times 4, well, I times 4 plus I squared. And this is 16 minus 1, because I squared is minus 1. This is 15 plus I 8. There you have it. And then finally 1 divided by I. We don't want I as divisor, so we'll put it in the front. Complex conjugate doesn't really work here, so we'll just multiply it by I itself, which is I divided by -1 equals -I. Now this is the final exercise, then I'll explain powers. 1 plus I cubed equals. Now the basic formula for a plus b cubed is a cubed plus 3 times a squared times b plus 3 times ab squared plus b cubed. If you don't know this formula, I suggest you remember it. It comes forth from the binomial theorem. It's quite handy sometimes. So a is 1, so it's 1 cubed plus 3 times 1 squared times b, so times I, plus 3 times 1 times I squared, and then we have plus I cubed. Now this will give us 1 plus, this is 3y, or I3, plus 3 times 1 times I squared, which is -1. So we have 1 minus 3, so it's -2. And we have the I in front, so if you remember how exponents work, I cubed is nothing else but I squared times y, so just -y. And now we have this, it's 3 minus 1, so it's plus 2y. Now you see in the problems I gave you 4 plus y squared and 1 plus I cubed, you can solve them by using the binomial theorem, like I said, but for higher exponents this will become really tedious and you'll probably make some errors, and we don't really want that. Now, if you didn't solve it like I did and you used the polar form, great thinking, because that's the next step. So if you want to calculate powers of z to the n, you have to use the polar form, so 3 times e to the y theta to the n equals r to the n times e to the y times theta n. You just apply the normal rules. Now for what is the square root actually? A square root, so 2, square root of 2, that's just 2 to the power 1 over 2. So we can use this in a form and rewrite roots as z to the power 1 over n. And now this will give you r times e to the y theta to the power 1 over n. Now we can just use this, because if I give you this equation, let's think about it. X squared equals 1. Now, of course, x equals 1, but x can also equal -1, because -1 squared is still 1. And this is kind of the problem with roots, because for an nth root, now this is kind of the problem with roots and complex numbers, because for every nth root, there are n solutions. And if you look at them in Gauss's plane, if the first solution is here and it's as a square root, then the other solution will be here. This is pi radians. Now, if it's a cube root, it'll be more like this. So 2 pi divided by 3 is 2/3 pi. And you can see, well, at least I hope you can see, there's a pattern in here. And if you connect these, you have a shape. Now for the formula, of course the r is gonna be to the power of 1 over n, or if you want to write it like this, the nth root of r times e to the y times. Now, this is a tricky part. It is theta divided by n, but it's also not only theta, it's plus 2 pi times k. K is a whole number. 2 pi k divided by n, and n is the n is here from the power, and k is just any number which is whole. So -1, +2, these are all just numbers. And with this formula, you'll find all the roots. Now I'll give you some more problems. Z squared equals -16. How do you solve this? Z equals square root of -16. You can rewrite this as 4 times square root of -1, which is 4 times I. But remember, 2 solutions. So if you're just gonna do this, you're not gonna get it. So what you do want to do, and I know it sounds tedious, like, hey, I don't even have a plus y, why would I want to change the polar form? But it's better. Or you can just use your intuition. This is the plane. If this is -16, you have 4i here. This is pi radians, and here you have -4i. You can also do it like that. I do it like this, you don't have to. Now, the next one, z cubed equals 8. So z equals cube root of 8. Now, one answer is 2. We'll give it here, 2. And with the other ones is gonna be there. This is 2/3 pi. So this is gonna be 2 times e to the I of 2/3 pi, and this one is gonna be 2 times I to the minus 2/3 pi. There you have it. Now I hope you can solve these equations. Functions you might see during complex analysis. Now first, if you see z between vertical lines, this just means the value of r. This is called the modulus, and this is just the length of the point to the null point. Now another one you might see is z with a bar on top of it. This is the complex conjugate, and it's a minus ib. Another one is the im. You might say im of z is just the imaginary part, so it gives you b. And you also have re, which is the real part of z, and this is a. These are some common functions you'll see, and now you also know them. This was it. This was my explanation of complex numbers. I hope you understand them now, and I'll see you in the next video. Don't forget to subscribe and ring that bell, and also maybe leave a like. Thank you.